Right, so today we're going to look at arguments in terms of our logic unit. So this one is a bit of a heftier lecture. So if at any point you want to take a break and come back to it, that you're more than welcome to do so. This one does have quite a bit in it. So I know the last one was a little bit shorter, so this kind of balances each other out. So we're going to work on arguments, which is the last topic that we cover in this unit. Okay, so first our definitions, and a lot of these words you'll have seen before in other classes, so they should seem familiar to you. So an argument is a set of statements that's assumed to be true. So that's also referred to, the first set of statements is the hypothesis. So we have a set of statements that's assumed to be true. So our true statements are our hypotheses, and then we have a final statement, which we call a conclusion. So what we're looking for with an argument is to see whether that true hypothesis gives you a true conclusion. And if that happens, we say that it's a valid argument. If we have a true hypothesis, right, we always assume that our hypothesis is true, and our true hypothesis gives us a false conclusion, right, we say that it's an invalid argument. So kind of like our conditional. So remember our conditional, P implies Q. So we want the case where P is true to imply true. That's our best case scenario, a true hypothesis to imply a true conclusion. So we want our hypothesis to imply our conclusion. So this is essentially what our argument is. Hypothesis implies conclusion. We don't want true implies false. That's our invalid argument when we have true implies false, right? That's when we have an invalid argument. Our valid argument is when we'll have true implies true, but remember for our conditionals, we also had those weird cases where it started with false. False implies false or false implies true, and those both gave us true. So the same thing here, we're okay with that. So these are all our okay scenarios. These are our valid arguments because it follows our conditional. So everything that we're doing with an arguments is our conditional statements here. So it's our hypothesis implies our conclusion. Okay, so our first example here, and you can have as many kind of statements in your hypothesis. We just combine them all to get one big compound hypothesis. So for example, I can have P and Q and R implying another simple statement S, right? So all these three simple statements form my hypothesis, and this is going to imply my conclusion. So it's always hypothesis implies conclusion, right? Again, when we're connecting our simple statements or even compound statements for our hypothesis, so when we're working with our hypothesis, no matter what I'm connecting to be true, we always connect with ands. We always connect with ands. And the reason for that is the basis of our argument, our very first line here, is a set of statements that are assumed to be true. If I need all three of these simple statements, P, Q, and R, to be true, the only way I'm going to get all of them being true is to use ands. Right? If I put an or in replace of one of these ands, then there's the case that there could be a false in there somewhere. I need the case where all of them are true to imply a true conclusion. So it seems a little complex. Let's just get into some examples so you can kind of see how it lays out. So for our first kind of truth table example here, we're going to say, I'm just going to pop this one up here to give us more room. Our hypothesis is going to be P and not Q. So these two things, this is a comma here. So P and not Q. And then our conclusion, we're going to say is P and Q. Okay, so this is our argument here. So to set it up, the first thing that we're going to do is we're going to set it up in argument form. So argument form is hypothesis implies conclusion. So I need to get all of this information to look like hypothesis implies conclusion. Just like we did with our proving equivalence, you set everything up with a biconditional. So now I'm going to set everything up with that conditional statement in the middle, that conditional symbol. So my hypothesis, remember, each part of your hypothesis has to be connected with ands. So my left-hand side here, so I'm going to put it in a big bracket, is going to be P and not Q. So those are the two parts of my hypothesis that I have here. So either you'll see it connected with a comma, or sometimes you'll see each line, so you'll see them stacked on top of each other. Another common form of writing this, I don't know if I have it in here, I don't think I, another common form of writing this is you'll see hypothesis, P, not Q, and then you'll see conclusion, P and Q. That's just another alternate way of writing it. So I have P and not Q are the conditions for my hypothesis, and these are going to imply my conclusion. I'm going to also put this in a big bracket, P and Q. And again, I like to keep everything in big brackets on either side of my conditional or biconditional, so it's very clear what I have here. So this should be hypothesis implies conclusion. Okay, so this isn't a proof for a biconditional, so we're not looking for that tautology in the end. We're looking to see if there's a tautology in the end. Right? If I get that tautology with my conditional, that means that my argument is valid. If I don't get that tautology in my last one, then I don't have a valid argument. Whereas before, when we were proving, we couldn't say they were equivalent until we had that tautology. So it's always kind of wrapped around getting that full T column in the end, but two different ways. So let's set this up in our truth table. So again, it's just the same truth table as we've been doing since the beginning of this unit. How many simple statements do I have? I just have my P and Q, so I can fill that in first. So I have true, true, false, false, and true, false, true, false. Okay, so that's done. Then I can set up all my connectives. So working with my left-hand side, I have P, already have that. I need the negation of Q, and then I need the P and negation of Q. Okay, my right-hand side, I just need P and Q. And then my last column should be all, should be everything. So again, I'm going to have P and not Q implies P and Q. Okay, so filling in our columns here, negation of Q is just the opposite of what we had in our Q column. So false, true, false, true. P and not Q, so my first column and my third column, I'm going to have false, true, false, false. P and Q, I'm going to have true, false, false, false. So the implication here, so again, I'm looking at this one implying that one. So false implies true. Remember our conditionals. If it starts with false, if we have a false hypothesis, it doesn't matter what the second statement or compound statement is, it's going to end up being true, right? Because we start on kind of false premises. So we're going to have true. The second case is the only scenario where we get a false in a conditional, when true implies false. And then we have false implies false will give us true, and false implies false will give us true. So we have an invalid argument. And that's all that's needed to say is invalid argument, right? This false here tells me that this argument will not always be true. There is a scenario where my hypothesis will not lead to a true conclusion. So we have false. Okay, even though we kind of started with false for this one, it doesn't matter as long as it meets our conditional requirements. So we have a false, I don't have a tautology, my argument is now invalid. Okay, let's go into some more examples. Change back to blue. Okay, so for example C, are we on C already? A, B, yep, we're on C. Okay, let's do a bunch of conditionals here. So we have a hypothesis of P implies Q, Q implies R, and my conclusion is going to be P implies R. So if P implies Q and Q implies R, then P implies R. Right? Remember our if-then statements? So if I need to write this as my full statement here, right, so this is going to become, my hypothesis is P implies Q and Q implies R. And remember, when we're doing our hypothesis, they have to be connected with an and. Have to. And then we're proving an argument, so that's conditional to the hypothesis, which is P implies R. Okay, so this is what this is our argument. So this is the statement of our argument. So anytime you're starting a full argument proof, right, you can take whatever you have given to you, whether it's words, whether it's symbolic logic, whether it looks like this, you have to get it into your statement first. So I want to see something like this that shows me you understand the hypothesis is on the left, the conclusion is on the right, and it's connected with a conditional. So I want to see this. This would be 1 mark to get to this point. Then we're going to fill it in with your truth table and your last column and your conclusion, whether it's valid or invalid at the end. So we have 3 simple statements here, P, Q, and R. So true, 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 false, 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 false. Q will be 2 trues, 2 false, 2 trues, 2 false. And R will alternate true, false, true, false, true, false, true, false. Okay, then our connectives, excuse me. So we have P implies Q, Q implies R, P implies Q and Q implies R. Right, that covers my hypothesis. So I have my first condition, my second condition, and then put together with an and. So this column represents my total hypothesis. Then we have our conclusion, P implies R, right? This column represents my conclusion. And everything together, so I can put all, right? That's my conditional. So not biconditional. Biconditional shows equivalence. Conditional proves arguments. Okay, so then filling in all of my columns. P implies Q, so again, this is where I recommend using your fingers, going down through the row and saying them out loud as you go through them. True implies true, gives me true. True implies true, gives me true. True implies false, gives me false. True implies false, gives me false. And then I have false all the way down, so false is going to give me true, right? When I start with a false, it's going to be true for my conditional. Then Q implies R. So true implies true is good, true implies false is bad, false implies true is okay, false implies false is okay. True implies true, true implies false, false implies true, and false implies false. Okay, then I have my two conditions of my hypothesis connected with an and. So I need both of those values to be true, which we have in the top row and in the 5th row and in the last 2 rows. Okay, and then P implies R. So again, using your fingers, going back to the P column and the R column, true implies true is true, true implies false is false, true implies true is true, true implies false is false, and then anything that starts with false will give me true. And then all. So again, I'm using, here's my hypothesis, here's my conclusion, and I'm connecting with a conditional. So if these conditions are met, then the conclusion will happen. So true implies true, gives me a true. False false implies false gives me a true. False implies true gives me a true. False implies false gives me a true. True implies true. False implies true. True implies true. True implies true. So I get that tautology, which means that here we have a valid argument. Okay, so again, kind of going through what your marks layout would be for this. So you'll get it arranged in symbolic logic in this case. So you'll get a mark for putting it into your full statement, showing me the symbolic logic in argument form. You'll get your marks throughout the truth table, depending on how complex your argument is. You'll get your mark for getting to the correct last column, so whether it's valid or not, and it may not be valid, right? The last case we did not have a valid argument. This one we did have a valid argument. And then showing me what that means. So whether you're saying your conclusion is that it's a valid argument or an invalid argument. Okay, so let's go into a word problem. So we have our hypothesis and conclusion written in word form. So there's a few more steps added to this one, and then it's the same thing that we just did. So we just have to layer in these words and change it into symbolic logic. So the very first topic that we did in this course was using our words and changing it into our symbols. So our hypothesis here, we have the food is bad or the chef is late. If the chef is not late, then the food is not bad. The food is bad if and only if the chef is late. And our conclusion is the food is bad and the chef is late. Okay, so we have to change this into symbolic logic and then prove whether or not this argument is valid. Okay, so first thing, I need to decide what my simple statements are going to be. So my P is going to be, let's just use my very first kind of statement in here. The food is bad. So I'm defining my simple statements. So my first condition for my hypothesis is the food is bad or the chef is late. So I know or is a connective, so I can't include that. I can't include not or if then, right? These are all our connectives. I can't include if and only if, and I can't include and. Ooh, and there's a not here. So those are all the words that can't be included in my simple statements. But I do have another kind of component here. Q, the chef is late. So then I have P and Q. I'm going to go through all of my statements to make sure there's not an R or an S hidden in there anywhere. So I have the food is bad or the chef is late. If the chef is not late, then the food is not bad. So that condition uses both P and Q as well. The food is bad if and only if the chef is late. That uses P and Q. And the food is bad and the chef is late, again, uses P and Q. So I'm okay to continue using just P's and Q's here. So now I want to get this into symbolic logic form. So just like we had prior in our other questions. So my hypothesis is going to be 1, 2, 3 conditions, right? We have 3 conditions here for our hypothesis. So the first one, the food is bad or the chef is late. So changing that using our P's and Q's and using our connectives. So the food is bad is P or the chef is late, Q. Okay, our next condition, if the chef is not late, then the food is not bad. Right, so we have an if-then statement, so I know I'm going to be using a conditional. If the chef is not late, so the chef is not late is Q, but I have not late, so I have not Q. And then that was an if-then, so that's going to be the conditional to the food is not bad. So that's negation of P. Okay, that's my second condition. The third one here, the food is bad, that's P. If and only if, that's a biconditional. The chef is late, that's a Q. Okay, so this is what my hypothesis looks like. My conclusion, the food is bad, P, and The chef is late. Q. So this is my symbolic logic. Okay, so this is where you started with in the last question. So I will absolutely be giving you an argument in word form that you have to first identify what your simple statements are, define your simple statements, and then use your symbolic logic. So a key thing here, common mistakes, is not using the negations properly. Not is a connective, so when it's it cannot be in your simple statement. So you have to make sure that you pull not out of your conditions or out of your conclusion and use the symbol for not. Use the connective rather than having it in the simple statement. Your P cannot be the food is not bad. It has to be the food is bad because not is a word that's a connective. Okay, hopefully that makes sense for everybody. So moving forward, so now we have our symbolic logic set up. Next, we have to make that statement, right? That full statement for the argument. So again, big bracket for my hypothesis. Everything has to be connected with ands. So I'm going to have P or Q, and not Q implies not P, and P biconditional with Q. So that entirety is my hypothesis, right? And then an argument is connected with our conditional. And my right-hand side is P and Q for my nice short conclusion. Okay, so now we can fill in our truth table. So I'm looking to prove whether the truth of this hypothesis will imply the truth of my conclusion. Okay, so we have just P's and Q's. Well, that's nice and easy. True, true, false, false. And Q, we have true, false, true, false. Now to kind of put everything in there. So I know I'm going to need P or Q. Was that or for our first one? Yep, or. P or Q. I know I'm going to need not Q, not P. Not Q implies not P. Oh, you know what? We're going to need more columns here. I did not give myself enough columns. So what I'm going to do is kind of smush them together so you can kind of add them on in your own work. So I'm just going to divide this one in two. Do not P, not Q. Then we'll have P or Q, not Q implies not P. P biconditional with Q. And then we'll do P or Q and not Q implies not P. And because I'm connecting all of them with and, right, I'm looking for the case when all of them are true. I'm going to put all of them in one. P and Q. Actually, no, we have enough room. We have enough room now. Do those two. Then we'll do P and Q, and not Q implies not P, and P biconditional with Q. So this one is my hypothesis. That one covers everything on the left-hand side. Then we have P and Q. This is my conclusion. And so this is all. So this is my hypothesis implies conclusion. Okay, so try to be as neat as you can in these top columns. I know that it is a little difficult, and I know that mine does look a little sloppy as well. Do the best you can. As long as I can read it, I can kind of work through it with you. And if you're drawing your own in your own work, again, you can adjust your column size to give yourself enough room, or you can slant it and write it upwards, whatever you need. I just need to make sure you understand how to arrange your columns. Okay, so now let's prove this. So we have not P and not Q. Those ones are nice and easy. It's just the opposite of what the original column was. So false, true, false, true. P or Q. So connecting our first two columns with an or, we're looking for at least one true. Not Q implies not P. So we're looking for not Q implies not P. So false implies false will give me true. True implies false will give me false. False implies true will give me true. And true implies true will give me true. So make sure you're going in the correct direction here. If you go in the opposite direction, your argument is not going to be correct all the way through. Right? We need not Q implies not P. Conditional is the one where we have to be very cautious of order. All the rest of them, the order is not as important. Okay, P biconditional with Q. So now I'm looking where the two values are the same in the row for my P and Q column. So true biconditional with true gives me true. The middle two have different values, and the bottom two have two false. So we end up with true, false, false, true. Okay, now connecting my P and Q with my not Q implies not P, so these two columns here. Connecting with an and, so I need both values to be true. So I end up with true, false, false. Okay, and then connecting all three of those things together. So the one that we just did with the biconditional, so these two columns here. True and true gives me a true, false and false gives me a false, true and false gives me a false, and true gives me a false. Okay, P and Q. P and Q, true, false, false, false. So I can see that these are the same, so my hypothesis implies conclusion. So true implies true gives me a true, false implies false, false implies false, false implies false. So I get that tautology, which means we have a valid argument. So if all those conditions are met, so the food is bad or the chef is late, if the chef is not late, then the food is not bad. The food is bad if and only if the chef is late. So if all of those things are met, all those conditions are met, then the conclusion that the food is bad and the chef is late ends up being true. Okay? So again, quite a bit of work here. There'll only maybe be one problem on your test, and then this will come up in your exam as well. So we can do it from our symbolic logic, we can do it from words, and we have a couple extra things that go with arguments here. So sometimes logic statements are not going to use our straightforward words like and or not, or our connectives that we're used to. Sometimes our arguments will use words like none, some, and all. So for these kind of problems, it's more of a visual issue than a logic issue. So we use a Venn diagram. If you remember our Venn diagrams from our set theory, we're going to use Venn diagrams to help us establish the validity of these arguments. So our first example here is all cats have tails. All cats have tails. So when we're drawing a Venn diagram, and remember we start with a rectangle, and then we define what our sets are. So we label them with letters. But here I have to also define kind of what each of these words means. So I'm going to call C, capital C, the set of cats, all of our cats. And then I'm going to call T the set of things that have tails. The set of cats and things that have tails. So if I'm saying that all cats have tails, right, then I'm going to have a big circle for everything that has a tail, all the things that have tails. And if all of my cats have tails, then my set of cats has to fit into, right, has to fit into the set of all things that have tails, right? We could say here that if we're using set theory, that our cats is a subset of our tails, right? So all kind of shows our subset. Okay, and then if we do no cats have tails, if we're showing that in a Venn diagram, again, we have our rectangle. So we have all the tails. So if I'm saying that no cats have tails, then that means that my cats is outside of my tail circle. So this would mean that we have a disjoint. Right? These sets are a disjoint. And then if I wanted to use the word some of the cats have tails. Ooh, that's a bad rectangle. So our universe here, set of all things that has tails, some of the cats have tails. That means we're going to have an intersecting part. So these are some of the cats in my intersection. Okay, so we can use these Venn diagrams to account for words like all, no, and some. Right? All, no, and some. So when our arguments are a little bit more vague or they don't exactly say what we're discussing, you can kind of work that way as well. Okay, so to go through some more examples of that, I'm trying to find which one I wanted to do next with you. Oh, here we go. Perfect. I already wrote it in for you guys. So we have the statements from above, so we can define them into arguments. So the first thing we have to do, just like we did with our other word problem, you have to use you have to define what your circles are, or define what the sets are. So we need to define using these things that we have. So we have two conditions for our hypothesis here. We have all nice people wear black, all people that wear black are interesting, and our conclusion is all nice people are interesting. Okay, so let's say that N represents the nice people. Let's say B represents the people that wear black. And let's call I the set of all interesting people. Okay, so I've defined all my sets. So we have the nice people, the people that are wearing black, and the interesting people. Okay, so if I want to show this argument, when we do our Venn diagram, we only do the Venn for the hypothesis. So we draw the Venn diagram for the hypothesis, and then we check the conclusion in the Venn diagram. So give yourself a nice big Venn diagram. Give yourself lots of space. Right? We have the universe, the set of all people. So we have all nice people wear black. So again, that all is going to show kind of our subset. So we have all nice people wear black. So I have to show that all the nice people are fitting into the circle of all the people that wear black. So I'm going to have my nice people nice and small in the middle, and they're going to fit into all the people that wear black. Okay, nice people all wearing black. And then all the people that wear black are interesting. So we have to fit all of those people into the interesting circle. Okay, so again, we only do the Venn diagram for the hypothesis. Okay, and then we prove that the conclusion is correct by checking our Venn diagram. So now we say, does the conclusion fit in the Venn diagram? So my conclusion here is all nice people are interesting. So all the nice people are in the interesting circle. So is that conclusion met? Is that conclusion valid? Yes. So we can say this is a valid argument. Okay, everybody see how that works? So you're always going to do, if we're doing words with all, some, or no, right? You're going to do the hypothesis in a Venn diagram, and then you're going to check, is the conclusion valid with your Venn diagram? Does the conclusion fit into your Venn diagram? Okay, so let's do another hypothesis here. All students pass the test. No student passing is funny. All students are not funny. Oh, sorry. Okay, so our hypothesis here. So getting our circles, so identifying what our circles are going to be. Let me get back to blue here. So S is going to refer to students, all of our students that, we'll just do students, all of our students. P is going to be students, is going to be passing the test. F is going to be funny people. And I think that covers everything. Students, passing the test, passing students is funny. All students are not funny. Okay, so our Venn diagram here. Okay, so all students pass the test. So all of my students are passing the test. No passing student is funny. So all my students that are passing the test, they cannot be funny. So my funny is disjoint with my students and my passing, right? So not only does this say no students are funny, right? In which case S and F would have to be disjoint, but it doesn't mean that P and F would have to be disjoint. But I say no passing student, so P has to be completely disjoint with F. And then we have here, all students are not funny. So all of my students are not funny is my conclusion, right? So all students pass the test. Students are passing the test. Check, that one is met. No passing student is funny. So my students and my passing are disjoint from funny. Good. And then my conclusion here is all students are not funny, right? All students, so that's all of my students here, are not funny. So they are disjoint. They are disjoint, which means they're not touching. There's no student that's also funny. So yes, we have another valid argument here. If my hypotheses are laid out in my Venn diagram and my conclusion also fits with that Venn diagram, then I know I have a valid argument. Okay, it's important to remember that you're not drawing the conclusion, you're checking the conclusion. You're drawing the hypothesis. So your conclusion may not fit in with what you have here, and that's okay. It just becomes an invalid argument. Okay, one more, I think. Yep, one more. So we have all integers are real numbers. Some real numbers are negative. Some integers are negative. Okay, so back to blue. Let's let's identify what our circles are going to be. So let's call I the circle for all of our integers. Let's call R the circle for our real numbers. And let's call N the circle for our negative numbers. Okay, so it's important that you identify what your circles are. If you just put letters, how am I supposed to know what you mean, right? So please make sure that you're identifying what your circles are going to be. We can draw ourselves a nice big rectangle for our Venn diagram. So again, we're just drawing for the conditions of our hypothesis. So our first one, all integers are real numbers. So all of my integers are going to fit into my real numbers. That one is drawn. So some real numbers are negative. Some real numbers are negative. Some real numbers are negative. So we could put our circle here. So some real numbers are negative. So I could do that. And then if I go for my conclusion, some integers are negative. If I look using this diagram, so make sure you're looking, if I look using this diagram, some integers are negative. This diagram says no. There's no overlap between my negative numbers and my integer numbers, so therefore my conclusion here would be that it's invalid. However, I could draw my negative number circle like this. Right? This still makes this condition met. Some real numbers are negative. Yes, some of my real number circle is also negative. And then my conclusion here, some integers are negative, would be valid. So there is the case where there's some interpretation to how your Venn diagram is going to look. I won't give you any questions on your test or on your exam that aren't exactly clear, that there's one answer. Right? But there is the cases where it's a little bit interpretive to how you draw your diagram. And those are going to be the cases where we have some. Right? Some is a little bit iffy. So some real numbers are negative. So you would have that it's valid because we don't know whether or not the negative is going to overlap with our integers. So we're going to say that this argument is valid. Right? We don't know where the circle overlaps unless there was a statement saying that no integers are negative. We're going to assume that there's some kind of overlap. So we would say that this argument is valid. Of course, also knowing how numbers work in math, we could argue that this argument is valid. But some is the tricky one, so I do want you to be careful. You'll see more problems with our all and no, just because it's a little bit easier to see that. Okay, I think I covered everything that I wanted to do here. So your arguments are page 252, questions 1 to 38. So these ones are a little bit more challenging. So I do encourage you to try all of these problems, and I'll put some more in our review as well. Right, because there's different cases for how we could get these ones. So I want you just to look at all of the different ways we could write this one. Right, I feel like I want to show all three of these. So this is our one case where we have some intersecting. We could also have the Venn diagram where we have real numbers, integer numbers, negative numbers, or we could have real numbers, integer numbers. Oh, that was messy. And negative numbers. So there's three cases for this one. This one's valid. Some integers are negative. This one's invalid. And this one's some integers. This one's invalid. Right, so it just depends on how you draw it. So again, please be mindful of the words that we're using when you go through your homework questions. Questions 138, all your odd ones will show your Venn diagrams in the back. We'll show your proofs in the back using your truth tables. Practice, 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 and it will become easier. And again, any questions, feel free to email or come into our live sessions at any point throughout the week, and we can go through any problems that you would like. Otherwise, I will see you in our test or in our next lecture videos for the next unit.